Okay, so starting with Redcraft, what I want to do first is explain the data that I have shared with you. And sorry, my keyboard kind of collapsed here. All right, so the data that you should have gotten, I have 1A1Z and 1D3Z. 1A1Z is what I want to start with, and 1A1Z, I have two subdirectories there. One of them is 1 Hertz, where I have all the data for 1A1Z. It's synthetic, and added in there is 1 Hertz of error added to residual dipolar couplings. And what you see dynamic is where 1A1Z undergoes dynamics, and the RDCs that you get are RDCs that are averaged as a consequence of dynamics. I'm not going to worry about that this time. So if there's interest to see how you would treat this dynamical situation, we can do that later. But I'm going to start with 1HZ, 1 Hertz, 1A1Z simulated data. If you go there, what you will see, what you will need are the following files. It's called nmrbox20. And this is the residual dipolar coupling format information, how you communicate, and the requirement of Redcraft. So everything starts with a line of header that requires to have the amino acid designation of that particular residue. If you have 3-bond J coupling, you can put it there. For the most part, when we do our work, we kind of exclude this. We assume this doesn't exist. And then you have some comments in here, if you like, residue 1, residue 5, however, this is comments. So you can, this is required. This number, if you have it, goes there. If you don't have it, you indicate all missing data as 999. So if this was not there, you just put 999 if you don't have the J coupling. Then residual dipolar couplings that are reported for this particular residue are going to be atom, the residue number for the first, and so residual dipolar couplings is interaction between a pair of atoms. Therefore, you need to define the 2 atoms that are included in this particular interaction. So atom 0, residue 0 of residue aspartate. So with the atom name is carbonyl, connected to residue 1, atom N, and the observed residual dipolar coupling is this, and some associated indication of the error. So certainty on that measurement. The higher the number, it's a weight of that particular measurement. So the higher the weight, the more certain reliability of the data, the lower the number, the less certain and more erroneous data that is. And you collect everything that goes with peptide plane 1 in here, everything that goes with peptide plane 2 goes in here, peptide plane 3, and so on and so forth for every residue that you have data. When you have missing data, they're indicated by 999. So for example, for this particular proline, we have carbonyl nitrogen, NH, I'm sorry, NH is not there, CH is not there, C alpha H alpha is there, and there is this HAH that is intra-residue. We have it here historically, has been part of Redcraft. You can assume that information is almost, these days, people don't collect this information. So if it is missing, you can just put it 999 or not include those particular entries in the Redcraft input file, input data. And if you have data from multiple Lyman media, they are designated with the same name, nmrbox20, and you have the extension 1, 2, 3 to indicate the Lyman medium 1, Lyman medium 2, and so on and so forth. So this is Lyman medium 2. So bear with me. For any experimentalist looking at this, you probably are going to say, yeah, this is a complete set of data. Everything is all pretty nice there. I understand. I'm going to use this as an example to demonstrate the capabilities of Redcraft. And very quickly, if you're interested, we can go to 1D3Z with the experimental data. In fact, I can do both demonstrations with any of the sets. So if you guys are interested to just look at the experimental data, we can just cut to that one straight and spend the next hour and a half that we have just looking at the experimental data? What are your choices? If no preferences, I'm just going to go with 1A, 1Z. Okay, I'm going to continue with 1A, 1Z. 1A, 1Z serves as an important structure. We use it a lot in our development because it is actually not an easy structure. It's not a very well-behaved structure. And I'll show you why. Once you have the data, this is nefRDC1, nefRDC2. These are leftover from the old versions of Redcraft. This configuration file is something that you initially do not have, but the GUI will create it for you. I will tell you what this file is as we get into some of the features, and I'm not sure what this test is. I'm going to remove test. You can run Redcraft from command line, or you can run Redcraft with the GUI, which is what I'm going to do. It kind of makes some of the things more accessible to use. So the moment Redcraft GUI comes up, by the way, you guys can see this, right?
Yeah, yes, we can see that.
Great.
You've got one grape. Oh, there it goes. It refreshed.
Yeah. Are we good? Okay, so once you have uploaded, you have invoked your program, this GUI will pop up, and I'm going to walk you through some of the more bare essentials of what you need to have in order to get at least familiar with Redcraft. First, you need to open your workspace. So your workspace is where you want to go to actually perform your work. So at this point, I am already there, workshop, 1A, 1Z, 1Hertz complete. This is where I'm at. And Redcraft automatically, if you have a consistent naming strategy for your RDC files, it will automatically find the RDC prefix of your input data, of your RDC constraints. If not, you can just type it in here. This is where you execute stage 1. This is where you execute stage 2 to actually get a structure. This is not generate RDCs. It should be either analyze RDCs or generate structure. And these two tabs, I'm not going to worry about them today, although they kind of facilitate more extended analysis of your structure. So when you do this, some basic statistics of what kind of what data you have can actually present itself here. More importantly is this figure that you can take a look at it that shows you data density. I believe maybe it was Adam that asked the question of where is a good place to start. Now, in this case, you can see data, the number of RDCs per residue, actually peptide plane, is shown as a bar graph colored blue, and number of RDC constraints for from the second Lyman medium is in green. You can see that there are 6 for residue 1, there are 2 for residue 2, and so on and so forth. In the more experimental-based sparse data, you can envision this be far less with gaps in the middle, which what I'm hoping, I'm going to designate at least the last half hour to that particular study with the experimental data. So the very first step is to execute stage 1. So here you need to specify the name of your RDC data sets. You need to specify whether you're going to work with Ramachandran level 1, level 2. I'm going to level 2, Ramachandran level for glycines. Now, if you recall, if you're familiar with this, glycine constrained Ramachandran space is different, significantly different from many other amino acids. That's why we treat glycine differently. There's a cutoff I'm not going to talk about. I'm just going to go through the very, very basic operation of Redcraft. And then I'm going to come back and I'm going to show you some of these features and what they are used for. So leave this as none. And the first thing that you do, if this will be the list of all the files that are in that working directory, you'll see that everything is minimal at this point. You can say execute stage 1, and you can see that there are stuff begins to happen here. So Redcraft walks through residues 1 through residue end 82. And what it does, it creates the results of the first step. If you open, so you see that there is 1 dot angles, 2 dot angles, 3 dot angles. So for every set of peptide planes, there is a corresponding dot angle file. You can double click on it and you can see that essentially what this has done, this has created the list of all the possible phi's and psi's that connect peptide plane 1 and peptide plane 2, or the first set of phi psi's, and has evaluated all possible existing structures to fitness to RDCs and then ranked it. So residue 1 and residue 2 are connected optimally with phi psi of -60, 50 with the fitness of 0.06 to RDCs, whereas at the bottom of this list, you see dihedral 80, 100 with the fitness of 0.911. This
Hey,
is,
Ome, one
yes,
question.
yes.
So you mentioned that for starting from 1 to 2, 2 to 3, it will evaluate literally 100,000 different combinations. Has it done all that for the 89 residues?
So that number exponentially grows as we go forward as a number of different criteria. So let me actually, I'm going to comment on that in 1 minute as to
Okay.
how many evaluations are performed right now.
Okay, thank you.
Okay, so hang in there, but that's a great question to ask. Please, if I don't answer you, I hope to do, come back and ask me that particular question, right? So this, in this particular instance, because there are only 261 entries in here, it evaluated 261 different conformations of peptide plane 1 and peptide plane 2, evaluated everything in a 10-degree increment, and came back with this list. So at this point, it evaluated 261 conformations between residue 1 and 2. Let me reduce this in size and put this on the side. And it did the similar thing for, okay, so it kind of, and this is the result of connecting between 2 and 3, or simply dihedrals of residue 2. And this is residue 3. So if I was to just put the first 3 residues side by side. So you can see that in this particular case, connectivity, dihedrals of residue 1 optimally is -60, 50. The second one is 30, 90. Third residue is -60, -20, and so on and so forth. It has done all 82 instances of it. And you can ask the question of, or you can propose, great, we are done. So this is the optimal phi psi for residue 1. This is the optimal phi psi for residue 2. This is the optimal phi psi for residue 3. Why don't we just collect that across all these files and create a structure and we are done? Which is not true, which is where the second stage comes in. But let me at this point take a moment to see whether what we have accomplished so far is clear. I don't know who just asked the question, but at this point we have looked at residue 1, 2, which has evaluated 261 conformations. For residue 2 that connects peptide plane 2 and 3, we have evaluated 610. And for residue 3, we have evaluated again 261 distinct conformations. And this has been repeated across the entire structure of 82 residues. So approximately, it seems like we are about, let's say, 300 conformations per residue across 83. So whatever 300 times 83, that number of, let's say, 100. So it's approximately 30,000 different conformations have been evaluated and summarized here. Is this part clear what we have done?
Yes.
Ome, yes, that's clear. I just want to address one thing in the chat window here. It seems that a number of us are on VMs where Redcraft is not running. Mark is looking into that. It seems like the patch that he put in place with your updated version was possibly not applied to all VMs. He's going to give some information on that, and we can direct people to use VMs that have Redcraft installed. Looks like right now nitrogen and magnesium are working just fine. So for people that have real VNC open that want to follow along, if you connect to either of those machines, that should be fine. And I'll put other VMs in the chat window.
Okay, all right.
Additional.
In the meantime, let me maybe take a moment to provide a little bit more information on this particular instance. Let me just make sure this particular point is clear. So what you're seeing here is the number of dihedrals that connect residue 1 and peptide plane 1 and 2, or dihedrals for residue 1, after starting with Ramachandran level 2, after filtering for the J coupling that was in the file. This is what survives. And each one of them has been subjected for evaluation fitness to RDCs. Now, if you want to incorporate that information in there too, to demonstrate visually, put it all together, essentially this is what you have. So this, if you look at it from top view, is the Ramachandran angles, that space that survived. In the z-axis, you see fitness to residual dipolar coupling. So if you were to kind of like visualize this, you could see that generally speaking, the most optimal fitness seems to be right here with some potentially other ones there. But it will give you the complexity of the landscape of residual dipolar coupling. So at this point, if one was to venture and say, where is the most likely set of structures, it would be right here in this region that corresponds to the lowest point of this minimization. So what you see along the z-axis plotted is basically the third column. So I'm producing a three-dimensional plot of phi psi versus fitness to residual dipolar couplings, and you get this kind of essentially a landscape of what the structures look like. If everybody's okay with this part, I'm going to continue with stage 2. Okay. So in stage 2, we start by indicating start and end residue. And this is one of the point strengths of Redcraft and study of analysis of structure with residual dipolar couplings, where you can specify which fraction of the protein you want to study. Even though I have data for the entire protein, I can just confine my structure calculations from residue 10 to residue 15. This is not possible with NOEs. With NOEs, your residue 10 may be interacting and have a NOE distance connectivity to some other residue. So let me not stress those facts at this point. Let me just stay to Redcraft. But if anybody wants to know more, let me know and I'll focus on it. But at this point, I'm going to start from residue 1 to the end residue. The number of media, alignment media is 2. And this is the depth of search. So in this depth of search is basically where I indicate how exhaustive of a search I want to conduct. And what Redcraft is going to do is going to start with 1 dot angle, and it's going to take 2 dot angle. There is 260 possible connectivities of residues 1 and 2. And in 2 dot angle, there is 600 possibilities of connecting residues 2 and 3, and it's going to combine and explore all possible 260 multiplied by 600, which is approximately it's let's say 6 times 300. So it's going to be 18,000 different combination of phi size for residues 1, 2, and 3. So for 3 peptide planes that are defined by 2 sets of phi size, it's going to exhaustively explore all these combinations. This number indicates that of the 18,000 combinations, rank and select only the top 100 to go forward. So let me run this, and then I'm going to come back and show you what exactly it is doing. So at this point, I'm going to say execute stage 2. And you will see additional files begin to pop out here. So for every residue that's being extended, you're going to create a .out file, a PDB file, and 2 redcat files for further analysis. I'm gonna avoid talking about red cat files maybe until a later session, but let's look at 2.out what happens. So in this particular instance, for residue 1, the optimal connective torsion angle was negative 60/50, and the optimal torsion angle for residue 2 is 30/90. But after exhaustively combining everything in this list and everything in this list and ranking them, the most fit structure is actually, I'm sorry, so there are a couple features on here. Let me repeat this exercise. I didn't mean to turn on some of the features. I'm going to do this later. Redcraft remembers its state from previous run, so that way it executes the previous configuration file. So if you run this and look at 2.out again, you will see that even though negative 60, 50, 30, 90 would have been the optimal selection, but after combining data from the peptide planes 1, 2, and 3, you see that the most optimal combination is negative 60, 150, combining residue 1 and 2. And if you ask the question of negative 60, 150, where is it in this list? Let's see. So it's somewhere down there. So the entry that is selected to be optimal, it was actually buried as entry number 125 in the first list. And a similar thing is on the second list. So this is the degree of that one. This is due to the fact that we have corrupted the data by adding 1 hertz of random noise. The correct structure is buried somewhere deep. And the same thing for the second list, that it's minus 50, minus 60, and minus 50, minus 60 is in this list is also not the top entry, is somewhere buried in the list. After exhaustively looking at all the 18,000 combination, this set of 100 combination of phi size is selected to go to the next round to be extended by a third residue or a fourth peptide plane. Let me stop at this point. Am I clear what Redcraft is doing? If you want to ask me questions, please do. This is really the core of what Redcraft does.
So as you travel along the chain, so are you going to keep doing this exponential exploration, or are you going to
Exactly. Yes, this is going to continue, which basically the computational complexity of this algorithm would be, if it was unhindered, it would have been an exponential growth and it would be intractable. So all the features that we have implemented in this particular Redcraft, some of which I'm showing you, some of which I'm going to show you later, is to tame the exponential complexity of this particular approach and make it more manageable, such that you're making on one hand, you're performing deep enough search, but on the other hand is not intractable such that it exhausts the resources of your computer.
So that's a little confusing for me. So I want to, just to be sure, for example, if you added residue number 3 now to this,
right, exactly.
You will take the last table you showed me, 4 or 5 columns, like 1 and 2 has now the optimum on the top, and you will but you will take all those entries and then add with the search for number 3. So you are still okay. So you have produced a subset of 18,000 into something like 100. So
right.
That's how you are taming the exponential growth.
Exactly,
okay.
Right. That's precisely it. So in this particular instance, if you were to perform an exhaustive search between the 3 sets of data, there's 200 here, 600 here, 200 here, it would be 200 times 600 by 200.
Yeah,
and
exactly.
if you throw the 4th one in there, would be another 200, and that's exhaustively, if you exhaustively, it would be exponentially growing.
Exactly.
But by putting this limiting search depth, every time you conclude, you only select the top 100 and it tames the exponential growth.
Okay, now with this, can I therefore also understand or interpret that we are traveling down the funnel, which you showed in the first slide?
Yes, it is related to that.
Okay.
Yeah, exactly. So any more questions? Going once, going twice. So let me see what this is. Yeah. So at this point, we have processed one dot angle, two dot angle, condensed it into 18,000 structures, looked at them, evaluated all of them, and selected the top 100. So from this point forward, these two are done. And now we want to subject this one. We're going to grow the list of 2 residues, 3 peptide planes, with a third one by combining this list with the angles that connect residue for residue 3. So all of these 100 will be exhaustively evaluated by being combined with all of these 200 and something structures. So there's 100 here, 260 geometries here. So this will be 26,000 geometries will be evaluated, and only the top 100 will be permitted to go for extension. So will be this list, which is now a list of 3 sets of phi size. So it went from 2 sets, with the top one being -60, 150, -50, -60, be now replaced with -1, -50, 150, -60, -60, -50, -30. This will becomes the extended list. Now goes and combines with 4 dot angles to actually become 4 dot out that has 4 sets of phi size, and so on and so forth, all the way to the end of the protein, which is 82 dot out, which is a list of 82 sets of phi size with the final fitness to the experimental data. This is in its entirety what Redcraft is doing. And from this point forward, what I am showing you is just going to be all the bells and whistles that extend this particular capability. But if this is a critical part to understand what it is doing and how you can modify it for your own use. So what I want to do, I want to stop at this point and see if there are questions.
Home.
Yes.
So if this method is, if it is so deterministic, if it is proceeding like that, now I want to understand Adam's question: why is it important to start from a part of the protein whereas maximum number of rich data of RDC you said? Why will it matter? It looks like this is an exhaustive enough algorithm.
So when that is correct. So when in instances like this, where there is no gap in the data or no low density, it really doesn't make a difference. Okay. But in some instances where, for example, 3 or 4 residues, let's say, for example, I'm working on something that residues 1, 2, 3, 4, the first 4 residues have only 2 RDC data, or maybe even 1 RDC data, followed by residue 6, 7, 8, 9, which has 6 RDCs. Now, the less data you have, the deeper search you must conduct. The less data you have, the more ambiguity in your structure of structure prediction. Okay. So it is better to start from a region where you know the data. Behind the scene, what I'm not telling you, there is this phenomenon of, there is this entity called order tensor. So really everything in the world of residual dipolar coupling really ultimately goes back to calculation of order tensors. Right. It is better to calculate an order tensor based on a region that has more data than based on the region that has less data, and therefore more ambiguity in calculation of the order tensor. Okay. That's really the principle of it, but I think that your question will be better answered when I go to the actual experimental data where there is gap of data. Okay, great. Right? Yeah. But if, so I'm waiting to hear from others to see if this makes any sense to people, and if there is not, then I'll show you the rest of it. Okay, so Redcraft performs this combinatorial approach, and along the line, it creates this these dot output files, which basically you can use to see how data is growing. And of particular importance for now, I want to bring your attention to this thing that we call this graph that we call dynamic profile. And let me go to something that has a little bit more data. So at 21, at residue 21, whereas 21 sets of phi size in here, this is essentially what the profile of our analysis looks like. So at 2.out, the best fitness that was available in that file was at 0.32 fitness to RDCs. The worst one, meaning at the bottom, at the very end of that 100 surviving in 2.out, was at 0.44. And if you observe this pattern as a protein structure grows, you will see it's indicative. So I want to bring your attention to that. That's what you're going to use in order to diagnose what is happening with your protein structure calculation, specifically whether you were successful or not, specifically whether there's internal dynamics violation of any of the assumptions. It's important to look at this, but at this point, I haven't told you what to look for. Be aware it exists, and I'll tell you more about it later. So at the end of this really shallow search without any bells and whistles attached, the question is, how well did it do? So at every point as your structure is growing, so let me go to 20. At this point, for example, at 28, this is what your structure would look like. And if you are interested in finding what is the structural similarity, so what I have included in here, you can go one step up, and 1A1Z protonated from PDB. If you collect it here, you can see if I say align 28 to 1A1Z, you can see at this point my structure is about 0.8 angstroms away. You can see what happened at 40 or 47. You can repeat this exercise again. And align your structure 47 to 1A1Z. And I don't know if you guys are familiar with PyMol. So PyMol, you can say align structure to structure, and based on sequence, and puts it in the right place and calculates backbone RMSD. The backbone RMSD that it calculates initially is 0.94, but it throws away some outliers in order to improve backbone RMSD. So I am primarily interested in this. You can look at this. Some people look at this and say, yeah, so a number of atoms were excluded. These are probably at the beginning, at the end, some outliers. But I am primarily going to go with this number, which if you wanted to just operate with that number, you just put a 0 at the end of your line. And so at this point, my structure is 1 angstrom away from the actual structure. So a couple of things to note in here that I think was a surprise to me and should be a surprise to the community. Your phi size are confined to 10-degree increment to a grid search. So with confinement to a 10-degree grid search, I managed to find a structure that is less than an angstrom away from the actual structure. So confining your structural calculations to a grid search of 10 degrees really does not compromise the quality of your structure. My peptide plane geometries are absolutely perfectly ideal. What comes out of, I believe we have used charm 90 something force field. I don't remember which force field we have used, but our peptide geometries are absolutely perfect. Nothing has been violated. My omegas are strictly 180 degrees. My phi size strictly stick to Ramachandran level 2. Bond lengths are absolutely ideal. So literally, if you were to take the structure and run ProCheck, run a variety of structure checking on this thing, you would find from very many perspectives, it's perfect. And it's the point of operating in the rotamer space. So And the question is how well did it do at the end? And we can look at that. And you can see so at this point is 1.7 angstroms away from the actual structure. So I like to stop at this point and see if there are questions I can answer on where your interests are. I can at this point demonstrate some of the more capabilities of Redcraft. Or you can, if you like, we can just jump straight into experimental data and explore some of the challenges that you may face. What I presented here was the most superficial search in Redcraft. I mean, I calculated the entire structure of the protein in a matter of seconds. And this may come as a surprise. It's partly because of this nmrbox really has really beefy hardware. And at the same time, it's just the data was easy. This was an easy case.
So Homik,
Yes.
So the search depth it shows to be 100. If I increase that, will this impact, do you think, the final deviation
Yes.
you showed in the PDB overlay?
Right. It will. So we can conduct that because at this point, so let me clear everything. So at this point, if you want to start a new run, you can clear everything, which clears everything regarding to stage 2. You don't have to repeat stage 1 unless you want to repeat stage 1. So at this point, you can increase your depth search, let me say 200. What it is going to do, if it's going to be, you will notice that it is running a little bit slower, but the entire structure will be calculated. If there was room for improvement, it would find a better structure. So at this point, I'm going to let it run.
So while it is running, let me also ask. So you said about this interesting thing. You could select a small segment and optimize instead of the whole protein.
Exactly.
So just again, as an academic understanding, so if I were to do this, let's say I just conceptually divide my, let's say the protein into these different alpha helices in my mind, and then I just do the optimization, the end result will be different, or how much different than doing exhaustive 1 to 82?
Yeah, so I'm not sure. So let's stay away from the exhaustive search, because if we were to do the exhaustive search, it's a very intractable problem. Nobody has ever done that to see what happens. So I don't know. But you can very well, so let me just demonstrate that feature if you're interested in seeing this. Let's say for whatever reason, let me show you another feature. Okay, so I think directly to your point, if nobody else has any request, I'm going to basically take this as the new direction. I will come at the end of it, really the power of what we are doing is exposed when we are actually analyzing the experimental data.
Yep.
And so, which is something I want to do. I want to reserve the last 30 minutes of this presentation for that. But in the interim, I am happy to take it in different directions. If there is no request, I'm going to go in this particular direction of, let's say my protein is fragmented and I need to do a fragmented study of it.
Right.
What will happen? All right. So, yeah.
Can I ask about the exhaustive search and splitting up the protein? If we split it up into something like groups of alpha helices as suggested, would it be reasonable to restrict an exhaustive search to regions without a defined secondary structure?
Yeah, absolutely. So at this point, I am kind of approaching as if you had no prior knowledge of anything. So if you did have a prior knowledge, for example, let's say residue 5 is going to be alpha helical. Let's say you know that. So all you need to do is just manually or write scripts. We have scripts to do this. This 6 dot angles is a file that you can edit. So you can go in here and you say, okay, so anything, any of these angles that's outside of alpha helical, we're gonna exclude. Throw it out and just confine it to alpha helical regions. And that way, speed up your search mechanism and you will have a more successful search. Did that answer your question?
Yep.
Yeah, so this is the part that you can inject any prior knowledge that you have. And in fact, if one of the things that we have developed is a deep mining of PDB, where you can give it a sequence and you will search the PDB and will come back based on sequence, will tell you what set of phi size is observed in PDB. And we have also scripts that will take that information connected as a substitute for stage 1. So in stage 1, you may not want to proceed based on the entire Ramachandran. You might want to limit it based on secondary structural prediction of just being alpha helical. Or you may want to proceed based on evolutionarily what the following sequence, what possible dihedrals do you see in PDB, and collect those and search over those. You could connect this to Talos. If Talos comes back and say certain region is alpha helical, you can connect it to that. So I don't know. Yeah, you can do all of those. So Redcraft is done now with a search of 200. You can confirm this is what is happening by looking at each one of the .out files. I'm gonna use the following Unix command to show you. If I do a word count on all the .out files, you will see that all my .out files are 200 lines long, because the depth search was 200. What I can do, I can say, I don't want to study my entire protein. I just want to study, I don't know, let me clear everything here. I want to study residue 10 through 22. And I have done stage 1, so stage 1 needs to be in place. Then I want to execute this. And you will see that there is no activity for residues 1 through 10, but you see, so you can see 11 .out, you see 12 .out, and so on and so forth. And you're going to go, the algorithm is going to go all the way to 22.pdb. This is my 22. And the question is, how well did I do in comparison to the actual structure? And you can align it. It's within 0.72 angstroms. And let's say for some reason you want to now study only residue 40 to 42. And you can calculate that. And you can load it into your into your PyMol. It was in here, and it was called, what would it be called? 42 dot. Sorry, this is short enough that I'm not sure if it's going to be meaningful. I'm going to say 40 to 52. So I want to get 52.pdb. That's this one. And I want to align 52 to my 1A1Z0. So it's both structures fit well. For those of you, I believe where this question is going towards study of dynamics. So if you want to know these two helices are undergoing dynamics with respect to each other, this would be the exact way to do this. And then you would further embark on red cat analysis to get order tensors from the two domains to see, are they rigid with respect to each other or are they dynamical with respect to each other?
Okay.
And that's all the stuff that I would cover if you're interested in the dynamical treatment of the structures from residual dipolar couplings. Let me show you a couple other features, and soon I'm going to jump on So I'm going to redo everything in here. Um,
Home,
yes,
one last question.
sure.
So this small fragmented optimization we said did, how well it works for the loop region?
So if you just do the loop region, you mean loop region by itself, like 2 or 3 residues that are in a loop region, or do you mean 2 segments that are connected by a loop region?
No, just the loop region. Let's say about 5 residues. In this structure, you have something about 4 to 5 residues that are between connecting 2 alpha helices.
Right.
So I'm just curious. So if I just were to optimize for that, I don't know the number, which numbers are they, but
Right. So let's say you just want to study a fragment of the protein that's small fragment, not like 10, 20 residues, more like you just want to look at 5 residues.
okay.
In order to gain confidence, especially to be able to tease out dynamics, and come up with the structure if the loop region is relatively rigid or whether it undergoes significant amount of dynamics,
Yeah.
you kind of need to make sure that there is sufficient amount of data in that region.
Okay. Yeah.
If you do, and as a general rule of thumb, I'm going to say 2 RDCs per residue from 2 alignment media.
Okay.
All right, so NH, C alpha, H alpha, for example, per residue from 2 alignment media. You should be able to tease out dynamics and whether your structure is really a structure or not. Any additional data is, of course, kind of like extra gravy.
Okay. Okay.
All right, so let me just go over some of the things that a skeptic would say. I'm going to drop this down to 100 again. So there are 2 things that you can enable here, actually 3. One of them is that when you look at your data, you may decide this particular region seems to be low in data density than the rest. So the depth search, because this region, the region that has higher data is already well defined, is going to work. You need to have lower depth search here. But in order to compensate for the quality of data or the quantity of data, you compensate by doing a more thorough search, more exhaustive search, which basically equates to depth search. So you can either at this point introduce, add a search depth at residue, I don't know, 10, perform a deeper search, which becomes kind of more customized depth search. You can do this. But you can do this, but usually this is not useful when you engage this decimation. So let me give you decimation. So decimation, what it does, if you recall my one dot angle and 2 dot angle, collectively, it was evaluating 18,000 structures, of which only 100 of them were permitted to go forward. So 100 out of 18,000 is a very small fraction. And the fear is always in that 18,000 discarded structure, the actual structure is there. Once it is discarded, you just can't get it back. One option is to have a more extensive depth search, but that makes the algorithm to be intractable. In order to have your cake and eat it too, we have this enabled decimation. So 100 structures of the depth search automatically are exempted and they are selected to go forward for elongation in the next round. Of the remaining discarded structures, so structures 101 all the way to 18,000 that would have been discarded, the algorithm performs the following routine. First, it collects all the structures, all the remaining 18,000, 17,900 structures, and bunches them into clusters that are within 3 angstroms of each other. That's this number. And then it establishes a threshold of, let's say, one hertz. So everything that it is within this fitness to RDC, for each cluster that is within 3 angstrom, 1 will be selected to go forward. all the cluster representatives that have a fitness of RDCs less than a cutoff will go forward. And if you populate this number, then only the top 1,000 selected additional structures will go forward. Otherwise, it will be exhausted. So and this is the range where decimation applies. So I'm going to turn this on, execute it, show you what it does. And from that point forward, then I'm going to jump onto 1D3Z. And I know I have little time. I know this is not exactly clear, but if you like to, I can spend more time maybe when I'm working with the experimental data, or talk to me after this, or get a hold of me, or read manuscripts that we have published this work. So in the absence of decimation, every one of the .out files would contain 100 structures going forward. Here I have said, cluster everything, all the structures within 3 angstroms of each other, select the representative, and as long as their threshold is within this allotted RDC fitness for residues 1 through 82, give me everything. This one, you're of course free to do any, like here's an example, residue 3, residues 4 through 6, and residues 9. Here I'm going to just say residues 1 through 82, and I'm going to go back to my basic, and I'm going to just say clear everything. And I'm just going to demonstrate this for residues 1 through 12 and execute stage 2. You will notice that the execution of stage 2 becomes a little bit slower, but in return, what happens here, where before the size of each one of the progressively growing .out files was fixed at a depth search, if I do a word count star.out, you will see that you're dynamically adjusting. So it starts with 100, it gradually grows, and during the regions that there's less data density, this population allotance increases, and at some point it decreases again. So it dynamically adjusts itself. And it's really a function of what you do here. So if I make my cluster smaller, so for example, let's say 1.5 angstrom cluster of structures go forward. Let me just, so let's say 2 angstrom, and in here, instead of 1 hertz, I make it a bigger one, everything with 3 or higher, then more number of structures that would have usually been eliminated are going to be permitted to go forward. This is one feature. The second feature is inclusion of any kind of other scripts that you may have included in here. So Redcraft, at the end of appending a fragment with any one given residue, stops and executes this particular script. This script can be anything you want it to be. It could be a minimization in Explore. It could be anything you want. In our case, is a script called unconstrained. It's a minimization script. So I can include this, which what it is going to do, I'm going to return these to its original values and show you, for example, I don't know, let's say 5 .out, or let's say just 3 .out, it would be, or 4 .out, is you can see that all the numbers are still adhering to 10-degree grid sampling. If I include this unconstrained optimization of the dihedrals, repeat my run, sorry. And if I was to go and open 4 .out, you would see that there is a population of my dihedrals that are no longer sticking to 10-degree increments, is because essentially at every periodically after the growth of the fragment, we stop and we take a selection of the number of these dihedrals that are subjected to further Levenberg-Marquardt minimization to break away from that 10-degree grid search in order to produce more continuous numbers of dihedral angles. So I'm entirely, I entirely accept if you don't understand that part didn't come across right. But it basically helps to break away from the 10-degree grid search constraints. And at this point, if you were to look at 12.pdb and compare it to the actual structure, you will see some minor improvement in the structure of the protein. So it works well. I say, let me stop at this point. Let me entertain questions. If there's any part of this that you didn't understand, this latter part of it, I'm happy to answer again. But I want to switch to 1D3Z. But let me stop and see what are your questions at this point.
Okay, Homei.
Yes.
So the having the cake and eating part, adding the decimation. So is there a thumb rule? It's a great feature you added. Is there a thumb rule when you normally need to use it? I mean, it is tempting to use it. Just turn it on.
Yeah.
Because
so
anyway,
no, I agree. It's really all of these bells and whistles that I'm showing you is in order to make Redcraft fit to your hardware. So
okay.
Generally, you want to run this. So Redcraft on even the fastest machines, even right here on this particular platform, nmrbox, I can run it with parameter sets because it is exponentially growing in complexity. I can set up its parameters that's going to consume all the 170 gigabytes of RAM and all the CPU power. So the question is, how fast do you need this program? Do you need the results given your hardware constraints?
Okay.
And from there, you tinker with the parameters to make it fit into your program.
Okay.
And if there are, of course, indications that Redcraft is having a hard time folding your protein for you. Did you want to see an example of problematic folding?
Yep.
Yes, please.
That would be great. Yeah.
So let me run this 1A1Z is an example of that, actually, even though it's synthetic data, but it actually works for you. So let me start it all the way from the beginning. I'm gonna, for now, as a point of comparison, let me see what I have here. So in 12.out, make a note that my best structure here has a fitness of 0.5.
Okay.
And make a note that I have generated data knowing that I have 1 hertz of error is injected into my residual dipolar coupling. So in theory, my fitness should always be less than 1 hertz, never more than 1 hertz. So let's repeat this exercise. Instead of Ramachandran space 2, I'm going to do 1, and I'm going to clear my angles, and I'm going to start my execution. So I am changing nothing other than my Ramachandran constraints. And in here, I'm going to go again with the entire protein. I'm going to stick to 100, which previously I had created a successful structure, and I'm going to turn all these off just to demonstrate when you run into problem. So stage 1 is completed by using only Ramachandran space, which means if you go and look at any particular angle file, you're going to see far less. Instead of 600 or 200 entries, you're going to see in the order of 50 or 60. So you're going to see, in this case, for example, there's only 117 entries. Is because my Ramachandran space was more constrained. So at this point, I have turned off decimation, everything else, and I'm going to run my program. Let me clear everything, and then I'm going to run, use all residues, and do stage 2. The program zips along, and let's just wait and see what we get at 82. And again, this exact exercise, when I repeated it with the Ramachandran constraints of level 1, it gave me a structure that it was about 1 angstrom away from the actual structure, these exact settings. Here now, so if I was to go to 82 and bring up my structure, you will see that it is just visual inspection will tell you that this is not a good structure. And if you like, I can go through the exercise of calculating backbone RMSD to the actual structure, but it's going to be high. And the primary reason why this is happening is because 1A1Z, there has some particular spots in it that the dihedral angles are outside of Ramachandran 1, in fact, very well outside of Ramachandran 1 and barely in Ramachandran space 2. Now, the question is, when would you know such problems have arisen? And that would be by looking at the output file. And first, you will see that the fitness to RDCs is well above your expected error. So you kind of need to have a handle on what is the quality of your data. And if you were to look at this a little bit more in detail, you will see there are these bumps. First, there is this huge bump that occurs at approximately residue 9, 10, 11, 12, 13, 14. There's another bump here. There's another bump here. These bumps are indicative of the regions where Redcraft assumptions have been violated. And the assumptions are either your peptide plane is not as suspected, so it may be in a, it may be the alternate from transfer may be in cis conformation. It could be that your Ramachandran space is too constrained, or it could be that you have dynamics. Dynamics discussion is next time if you guys want. But this would be, in fact, if you go and look at 1A1Z at residue, whatever this is, and whatever this is, and possibly these, there is a Ramachandran violation. And in fact, Ramachandran is wide. So then you expand your Ramachandran space, and from there you repeat the exercise, and everything works just fine.